The decibel is a logarithmic unit used to express the ratio between two values of a physical quantity, often power or intensity. One of these quantities is often a reference value, and in this case the decibel can be used to express the absolute level of the physical quantity. The number of decibels is 10 times the logarithm to base 10 of the ratio of the two power quantities. 1 decibel is 1/10 of 1 bell. The bell is named in honor of Alexander Graham Bell, but is seldom used. The definition of the decibel is based on the measurement practices in telephony of the early 20th century and the bell system in the United States. Today, the unit is used for a wide variety of measurements in science and engineering, most prominently in acoustics, electronics, and control theory. In electronics, the gains of amplifiers, attenuation of signals, and signal-to-noise ratios are often expressed in decibels. The decibel confers a number of advantages, such as the ability to conveniently represent very large or small numbers, and the ability to carry out multiplication of ratios by simple addition and subtraction. A change in power by a factor of 10 corresponds to a 10 decibels change in level. A change in power by a factor of 2 approximately corresponds to a 3 decibels change. A change in voltage by a factor of 10 results in a change in power by a factor of 100 and corresponds to a 20 decibels change. A change in voltage ratio by a factor of 2 approximately corresponds to a 6 decibels change. The decibel symbol is often qualified with a suffix that indicates which reference quantity has been used or some other property of the quantity being measured. For example, dBm indicates a reference level of 1 mW, while dBu is referenced to approximately 0.775 volts RMS. The definitions of the decibel and bell use base 10 logarithms. The NEPA, an alternative logarithmic ratio unit sometimes used, uses the natural logarithm. History: the decibel originates from methods used to quantify signal losses in telephone circuits. These losses were originally measured in units of miles of standard cable, where 1 MSc corresponded to the loss of power over a 1-mile length of standard telephone cable at a frequency of 5,000 radians per second, and roughly matched the smallest attenuation detectable to the average listener. Standard telephone cable was defined as a cable having uniformly distributed resistance of 88 ohms per loop mile and uniformly distributed shunt capacitance of 0.054 microfarad per mile. The transmission unit was devised by engineers of the Bell Telephone Laboratories in the 1920s to replace the MSc. 1 TU was defined as 10 times the base 10 logarithm of the ratio of measured power to a reference power level. The definitions were conveniently chosen such that 1 TU approximately equaled 1 MSc. In 1928, the Bell system renamed the TU the decibel, being 1/10 of a newly defined unit for the base 10 logarithm of the power ratio. It was named the Bell, in honor of their founder and telecommunications pioneer Alexander Graham Bell. The Bell is seldom used, as the decibel was the proposed working unit. The naming and early definition of the decibel is described in the NBS Standards Yearbook of 1931. Since the earliest days of the telephone, the need for a unit in which to measure the transmission efficiency of telephone facilities has been recognized. The introduction of cable in 1896 afforded a stable basis for a convenient unit, and the mile of standard cable came into general use shortly thereafter. This unit was employed up to 1923, when a new unit was adopted as being more suitable for modern telephone work. The new transmission unit is widely used among the foreign telephone organizations, and recently it was termed the decibel at the suggestion of the International Advisory Committee on Long-Distance Telephony. The decibel may be defined by the statement that two amounts of power differ by 1 decibel when they are in the ratio of 100.1, and any two amounts of power differ by n decibels when they are in the ratio of 10n, 0.1. The number of transmission units expressing the ratio of any two powers is therefore 10 times the common logarithm of that ratio. This method of designating the gain or loss of power in telephone circuits permits direct addition or subtraction of the units expressing the efficiency of different parts of the circuit. In April 2003, the International Committee for Weights and Measures considered a recommendation for the decibel's inclusion in the International System of Units, but decided not to adopt the decibel as an SI unit. However, the decibel is recognized by other international bodies such as the International Electrotechnical Commission and International Organization for Standardization. The IEC permits the use of the decibel with field quantities as well as power, and this recommendation is followed by many national standards bodies, such as NIST, which justifies the use of the decibel for voltage ratios. The term field quantity is deprecated by ISO. Neither IEC nor ISO permit the use of modifiers such as dBAR or dBV. Such units, though widely used, are not defined by international standards. Definition: the decibel is 1/10 of the bell, 1 byte equals 10 decibels. The bell represents a ratio between two power quantities of 10:1, and a ratio between two field quantities of 10:1. A field quantity is a quantity such as voltage, current, pressure, electric field strength, velocity, or charge density, the square of which in linear systems is proportional to power. A power quantity is a power or a quantity directly proportional to power, for example, energy density, acoustic intensity and luminous intensity. The method of calculation of a ratio in decibels depends on whether the measured property is a power quantity or a field quantity. Two signals that differ by 1 decibel have a power ratio of which is approximately 1.25892, and an amplitude ratio of. The bell is defined by ISO standard 80000-3 as Ln, 10, nepers. Because the decibel is 1/10 of a bell, it follows that 1 decibel equals Ln, 10, np. The same standard defines 1 np as equal to 1. Although permissible, the bell is rarely used with other SI unit prefixes than deci. It is preferred to use hundredths of a decibel rather than millibels. Power quantities. When referring to measurements of power or intensity, a ratio can be expressed in decibels by evaluating 10 times the base 10 logarithm of the ratio of the measured quantity to the reference level. Thus, the ratio of a power value P1 to another power value P0 is represented by LdB, that ratio expressed in decibels, which is calculated using the formula. The base 10 logarithm of the ratio of the two power levels is the number of bells. The number of decibels is 10 times the number of bells. P1 and P0 must measure the same type of quantity, and have the same units before calculating the ratio. If P1 equals P0 in the above equation, then LdB equals 0. If P1 is greater than P0, then LdB is positive. If P1 is less than P0, then LdB is negative. Rearranging the above equation gives the following formula for P1 in terms of P0 and LdB. Field quantities. When referring to measurements of field amplitude, it is usual to consider the ratio of the squares of A1 and A0. This is because in most applications power is proportional to the square of amplitude, and it is desirable for the 2 decibel formulations to give the same result in such typical cases. Thus, the following definition is used. The formula may be rearranged to give. Similarly, in electrical circuits, dissipated power is typically proportional to the square of voltage or current when the impedance is held constant. Taking voltage as an example, this leads to the equation where V1 is the voltage being measured, VO is a specified reference voltage, and GdB is the power gain expressed in decibels. A similar formula holds for current. The term root power quantity is introduced by ISO standard 80000-1-2009 as a synonym of field quantity. The term field quantity is deprecated by that standard. Examples. All of these examples yield dimensionless answers in decibel because they are relative ratios expressed in decibels. The unit dBW is often used to denote a ratio for which the reference is 1W, and similarly dBm for a 1 megawatt reference point. Calculating the ratio of 1 kilowatt to 1 W in decibels yields. The ratio of 2 in decibels is. Illustrating the consequence from the definitions above that has the same value, regardless of whether it is obtained from powers or from amplitudes, provided that in the specific system being considered power ratios are equal to amplitude ratios squared. The ratio of 1 megawatt to 10 W in decibels is obtained with the formula. the power ratio corresponding to a 3 decibels change in level is given by a change in power ratio by a factor of 10 is a change of 10 decibels. A change in power ratio by a factor of 2 is approximately a change of 3 decibels. More precisely, the factor is 103/10, or 1.9953, about 0.24% different from exactly 2. Similarly, an increase of 3 decibels implies an increase in voltage by a factor of approximately, or about 1.41, an increase of 6 decibels corresponds to approximately 4 times the power and twice the voltage, and so on. In exact terms, the power ratio is 106/10, or about 3.9811, a relative error of about 0.5%. Properties: the decibel has the following properties. The logarithmic nature of the decibel means that a very large range of ratios can be represented by a convenient number, in a similar manner to scientific notation. This allows one to clearly visualize huge changes of some quantity. See Bowed plot and semi-log plot. For example, 120 decibels SPL may be clearer than a trillion times more intense than the threshold of hearing, or easier to interpret than 20 pascals of sound pressure. The unit is an additive function, which means that the overall gain of a multi-component system, such as a series of amplifier stages, can be calculated by summing the gains in decibels of the individual components, rather than multiply the amplification factors. That is, log, or a bar a C, equals log, a, plus log, b, plus log, c. Practically, this means that, armed only with the knowledge that 1 decibel is approximately 26% power gain, 3 decibels is approximately 2 power gain, and 10 decibels is 10 power gain, it is possible to determine the power ratio of a system from the gain in decibel with only simple addition and multiplication. For example, a system consists of 3 amplifiers in series, with gains of 10 decibel, 8 decibel, and 7 decibel respectively, for a total gain of 25 decibel. Broken into combinations of 10, 3, and 1 decibel, this is, 25 dB equals 10 decibels plus 10 decibels plus 3 decibels plus 1 decibel plus 1 decibel. With an input of 1 watt, the output is approximately 1 W x 10 x 10 x 2 x 1.26 x 1.26 equals 317.5 W. Calculated exactly, the output is 1 W x 10/25 tenths equals 316.2 W. The approximate value has an error of only plus 0.4% with respect to the actual value, which is negligible given the precision of the value supplied and the accuracy of most measurement instrumentation. Advantages and disadvantages. Advantages: according to Meichke, the advantage of using a logarithmic measure is that in a transmission chain, there are many elements concatenated, and each has its own gain or attenuation. To obtain the total, addition of decibel values is much more convenient than multiplication of the individual factors. The human perception of the intensity of, for example, sound or light, is more nearly linearly related to the logarithm of intensity than to the intensity itself, per the Weber-Fechner law, so the decibel scale can be useful to describe perceptual levels or level differences. Disadvantages: according to several articles published in Electrical Engineering and the Journal of the Acoustical Society of America, the decibel suffers from the following disadvantages. The decibel creates confusion. The logarithmic form obscures reasoning. Decibels are more related to the era of slide rules than that of modern digital processing. Decibels are cumbersome and difficult to interpret. Hickling concludes decibels are a useless affectation, which is impeding the development of noise control as an engineering discipline. Another disadvantage is that quantities in decibels are not necessarily additive, thus being of unacceptable form for use in dimensional analysis. Uses: acoustics. The decibel is commonly used in acoustics as a unit of sound pressure, for a reference pressure of 20 micropascals in air and 1 micropascal in water. The reference pressure in air is set at the typical threshold of perception of an average human, and there are common comparisons used to illustrate different levels of sound pressure. Sound pressure is a field quantity, therefore the field version of the unit definition is used. Where pref is equal to the standard reference sound pressure level of 20 micropascals in air or 1 micropascal in water. The human ear has a large dynamic range in audio reception. The ratio of the sound intensity that causes permanent damage during short exposure to the quietest sound that the ear can hear is greater than or equal to 1 trillion. Such large measurement ranges are conveniently expressed in logarithmic units. The base 10 logarithm of 1012 is 12, which is expressed as a sound pressure level of 120 decibels re 20 micropascals. Since the human ear is not equally sensitive to all sound frequencies, noise levels at maximum human sensitivity, somewhere between 2 and 4 kHz, are factored more heavily into some measurements using frequency weighting. Electronics. In electronics, the decibel is often used to express power or amplitude ratios, in preference to arithmetic ratios or percentages. One advantage is that the total decibel gain of a series of components can be calculated simply by summing the decibel gains of the individual components. Similarly, in telecommunications, decibels denote signal gain or loss from a transmitter to a receiver through some medium using a link budget. The decibel unit can also be combined with a suffix to create an absolute unit of electric power. For example, it can be combined with m for milliwatt to produce the dBm. 0 dBm is the level corresponding to 1 milliwatt, and 1 dBm is 1 decibel greater. In professional audio specifications, a popular unit is the dBu. The suffix u stands for unloaded, and was probably chosen to be similar to lowercase v, as dBv was the older name for the same unit. It was changed to avoid confusion with dBv. The dBu is a root mean square measurement of voltage that uses as its reference approximately 0.775 ERMS. Chosen for historical reasons, the reference value is the voltage level which delivers 1 megawatt of power in a 600 ohm resistor, which used to be the standard reference impedance in telephone circuits. Optics. In an optical link, if a known amount of optical power, in dBm, is launched into a fiber, and the losses, in decibel, of each electronic component are known, the overall link loss may be quickly calculated by addition and subtraction of decibel quantities. In spectrometry and optics, the blocking unit used to measure optical density is equivalent to a 1B. Video and digital imaging. In connection with video and digital image sensors, decibels generally represent ratios of video voltages or digitized light levels, using 20 log of the ratio, even when the represented optical power is directly proportional to the voltage or level, not to its square, as in a CCD imager where response voltage is linear in intensity. Thus, a camera signal-to-noise ratio or dynamic range of 40 decibels represents a power ratio of 100 to 1 between signal power and noise power, not 10,001. Sometimes the 20 log ratio definition is applied to electron counts or photon counts directly, which are proportional to intensity without the need to consider whether the voltage response is linear. However, as mentioned above, the 10 log intensity convention prevails more generally in physical optics, including fiber optics, so the terminology can become murky between the conventions of digital photographic technology and physics. Most commonly, quantities called dynamic range, or signal-to-noise would be specified in 20 log dBs, but in related contexts the term should be interpreted cautiously, as confusion of the two units can result in very large misunderstandings of the value. Photographers also often use an alternative base 2 log unit, the f-stop, and in software contexts these image level ratios, particularly dynamic range, are often loosely referred to by the number of bits needed to represent the quantity, such that 60 decibels is roughly equal to 10 f-stops or 10 bits, since 103 is nearly equal to 210. Suffixes and reference values. Suffixes are commonly attached to the basic decibel unit in order to indicate the reference value against which the decibel measurement is taken. For example, dBm indicates power measurement relative to 1 milliwatt. In cases such as this, where the numerical value of the reference is explicitly and exactly stated, the decibel measurement is called an absolute measurement, in the sense that the exact value of the measured quantity can be recovered using the formula given earlier. If the numerical value of the reference is not explicitly stated, as in the decibel gain of an amplifier, then the decibel measurement is purely relative. The SI does not permit attaching qualifiers to units, whether a suffix or prefix, other than standard SI prefixes. Therefore, even though the decibel is accepted for use alongside SI units, the practice of attaching a suffix to the basic decibel unit, forming compound units such as dBm, dBu, dBar, etc., is not. Outside of documents adhering to SI units, the practice is very common as illustrated by the following examples. There is no general rule, with various discipline-specific practices. Sometimes the suffix is a unit symbol, sometimes it's a transliteration of a unit symbol, sometimes it's an acronym for the unit's name, other times it's a mnemonic for the type of quantity being calculated, or otherwise a general attribute or identifier about the nature of the quantity. The suffix is often connected with a dash, with a space, with no intervening character, or enclosed in parentheses, decibel, SM. Voltage. Since the decibel is defined with respect to power, not amplitude, conversions of voltage ratios to decibels must square the amplitude, or use the factor of 20 instead of 10, as discussed above. dBV, decibel, VRMS, a euro voltage relative to 1 volt, regardless of impedance. dBu or dBV, RMS voltage relative to. Originally dBV, it was changed to dBu to avoid confusion with dBV. The V comes from volt, while U comes from unloaded. dBu can be used regardless of impedance, but is derived from a 600 AI copyright low dissipating 0 a dBm. The reference voltage comes from the computation. In professional audio, equipment may be calibrated to indicate a 0 on the VU meters some finite time after a signal has been applied at an amplitude of +4 dBu. Consumer equipment will more often use a much lower nominal signal level of -10 dBV. Therefore, many devices offer dual voltage operation for interoperability reasons. A switch or adjustment that covers at least the range between +4 dBu and -10 dBV is common in professional equipment. dBmV, decibel, MVRMS, a euro voltage relative to 1 mV across 75 I copyright. Widely used in cable television networks, where the nominal strength of a single TV signal at the receiver terminals is about 0 dBmV. Cable TV uses 75 I copyright coaxial cable, so 0 dBmV corresponds to a 78.75 dBW or 13 nanowatts. dB 1/4 V or dBuV, decibel, I 1/4 VRMS, a euro voltage relative to 1 microvolt. Widely used in television and aerial amplifier specifications. 60 dB 1/4 volt equals 0 dBmV. Acoustics, probably the most common usage of decibels in reference to sound level is decibel SPL, sound pressure level referenced to the nominal threshold of human hearing. The measures of pressure use the factor of 20, and the measures of power use the factor of 10. Decibel SPL, a euro for sound in air and other gases, relative to 20 micropascals equals to a 10 of 5 pascals, approximately the quietest sound a human can hear. For sound in water and other liquids, a reference pressure of 1 I 1/4 Pascal is used. An RMS sound pressure of 1 Pascal corresponds to a level of 94 a decibel SPL. Decibel SIL, decibel sound intensity level a euro relative to 10 a 12 watts per meter 2, which is roughly the threshold of human hearing in air. Decibel SWL, decibel sound power level a euro relative to 10 a 12 W, decibel A, decibel B, and decibel C. These symbols are often used to denote the use of different weighting filters, used to approximate the human ear's response to sound, although the measurement is still in decibel. These measurements usually refer to noise and noisome effects on humans and animals, and are in widespread use in the industry with regard to noise control issues, regulations and environmental standards. Other variations that may be seen are dBar or dBar. According to ANSI standards, the preferred usage is to write LA equals X decibel. Nevertheless, the units dBar and decibel, A, are still commonly used as a shorthand for A-weighted measurements. Compared dBc, used in telecommunications. Decibel HL or decibel hearing level is used in audiograms as a measure of hearing loss. The reference level varies with frequency according to a minimum audibility curve as defined in ANSI and other standards, such that the resulting audiogram shows deviation from what is regarded as normal hearing. Decibel Q is sometimes used to denote weighted noise level, commonly using the ITU 468 noise weighting. Audio electronics, dBm, decibel, megawatt, a euro power relative to 1 milliwatt. In audio and telephony, dBm is typically referenced relative to a 600 ohm impedance, while in radio frequency work dBm is typically referenced relative to a 50 ohm impedance. Dbfs, decibel, full scale, a euro the amplitude of a signal compared with the maximum which a device can handle before clipping occurs. Full scale may be defined as the power level of a full-scale sinusoid or alternatively a full-scale square wave. A signal measured with reference to a full-scale sine wave will appear 3 decibels weaker when referenced to a full-scale square wave, thus, 0 dBfs, ref equals full-scale sine wave, equals -3 dBfs, ref equals full-scale square wave. dBTP, decibel, true peak amplitude of a signal compared with the maximum which a device can handle before clipping occurs. In digital systems, 0 dBTP would equal the highest level a processor is capable of representing. Measured values are always negative or 0, since they are less than or equal to full scale. Radar, dBz, decibel, Z, a euro decibel relative to Z equals 1 mm 6 Ma 3, energy of reflectivity, related to the amount of transmitted power returned to the radar receiver. Values above 15 a euro 20 dBz usually indicate falling precipitation. dBsm, decibel, M2, a euro decibel relative to 1 square meter, measure of the radar cross-section of a target. The power reflected by the target is proportional to its RCS. Stealth aircraft and insects have negative RCS measured in dBsm, large flat plates or non-stealthy aircraft have positive values. Radio power, energy, and field strength, dBc, dBc a euro relative to carrier a euro in telecommunications, this indicates the relative levels of noise or sideband power, compared with the carrier power. Compared dBc, used in acoustics. dBj, decibel, J, a euro energy relative to 1 joule. 1 joule equals 1 watt-second equals 1 watt per hertz, so power spectral density can be expressed in dBj. dBm, decibel, megawatt, a euro power relative to 1 milliwatt. Traditionally associated with the telephone and broadcasting industry to express audio power levels referenced to 1 milliwatt of power, normally with a 600 ohm load, which is a voltage level of 0.775 volts or 775 millivolts. This is still commonly used to express audio levels with professional audio equipment. In the radio field, dBm is usually referenced to a 50 ohm load, with the resultant voltage being 0.224 volts. dB 1/4 volt per meter or dBUVM, decibel, I 1/4 volt per meter, a euro electric field strength relative to 1 microvolt per meter. Often used to specify the signal strength from a television broadcast at a receiving site. dBf, decibel, FW, a euro power relative to 1 femtowatt. dBw, decibel, W, a euro power relative to 1 watt. dBk, decibel, kilowatt, a euro power relative to 1 kilowatt. Antenna measurements, dB, decibel, isotropic, a euro the forward gain of an antenna compared with the hypothetical isotropic antenna, which uniformly distributes energy in all directions. Linear polarization of the M field is assumed unless noted otherwise. dBd, decibel, dipole, a euro the forward gain of an antenna compared with a half-wave dipole antenna. 0 dBd equals 2.15 dB, dBc, decibel, isotropic circular, a euro the forward gain of an antenna compared to a circularly polarized isotropic antenna. There is no fixed conversion rule between dBc and dB, as it depends on the receiving antenna and the field polarization. dBq, decibel, quarter wave, the forward gain of an antenna compared to a quarter wavelength whip. Rarely used, except in some marketing material. 0 dBq equals a 0.85 dB, dBsm, decibel, m2, decibel relative to 1 square meter, measure of the antenna effective area. dBm a 1 decibel, m1, decibel relative to reciprocal of meter, measure of the antenna factor. Other measurements, decibel hertz, decibel, hertz, bandwidth relative to 1 hertz. For example, 20 decibels hertz corresponds to a bandwidth of 100 hertz. Commonly used in link budget calculations. Also used in carrier-to-noise density ratio. Dbov or dBo, decibel, overload, the amplitude of a signal compared with the maximum which a device can handle before clipping occurs. Similar to Dbfs, but also applicable to analog systems. dBr, decibel, relative, simply a relative difference from something else, which is made apparent in context. The difference of a filter's response to nominal levels, for instance. dBrn, decibel above reference noise. See also dBrnc. dBrnc represents an audio level measurement, typically in a telephone circuit, relative to the circuit noise level, with the measurement of this level frequency weighted by a standard C-message weighting filter. The C-message weighting filter was chiefly used in North America. The psophometric filter is used for this purpose on international circuits. See psophometric weighting to see a comparison of frequency response curves for the C-message weighting and psophometric weighting filters. dBk, decibel, K, decibels relative to Kelvin, used to express noise temperature. Decibel per carat, decibel, K1, decibels relative to reciprocal of Kelvin, not decibels per Kelvin, used for the GT factor, a figure of merit utilized in satellite communications, relating the antenna gain G to the receiver's system noise equivalent temperature T. Related units, mbm, mb, megawatt, power relative to 1 milliwatt, in millibels. 100 mbm equals 1 dBm. This unit is in the Wi-Fi drivers of the Linux kernel and the regulatory domain sections. NP or CNP, another closely related unit is the NEPA or centinpa. Like the decibel, the NEPA is a unit of level. The linear approximation 1 CNP equals 1% for small percentage differences is widely used finance. Fractions, attenuation constants, in fields such as optical fiber communication and radio propagation path loss, are often expressed as a fractional ratio to distance of transmission. Decibel per meter means decibels per meter, decibel per mile is decibels per mile, for example. These quantities are to be manipulated obeying the rules of dimensional analysis. For example, a 100-meter run with a 3.5 decibels per kilometer fiber yields a loss of 0.35 decibels equals 3.5 decibels per kilometer, 0.1 a km. See also, apparent magnitude, cent in music, decibel drag racing, equal loudness contour, noise, phon, Richter magnitude scale, signal noise, notes and references. External links. What is a decibel? With sound files and animations, conversion of sound level units, dBSPL or dBar to sound pressure P in sound intensity J, OSHA regulations on occupational noise exposure.